Which is, and there's various names for these. People will call them inertial probes, scoop probes, flow return probes. So we've been referring to it as a scoop probe. And the whole idea in a scoop probe or inertial probe is that if the direction of flow is towards a cylindrical object, you're going to build up a high pressure where the flow impacts. Well, because other people call them impact probes. So you're going to build up a high pressure at where the impact part happens. So Nayef has just joined. He's been coming in and out a couple of times. So with impact probes, the idea is to use the kinetic energy, the kinetic energy of the flowing process fluid to help to drive flow through the probe and allow it to be returned back to process. So we essentially use the kinetic energy in the pipeline to build a fast loop that doesn't require an external pump or some other device in the flow system to create differential pressure and drive flow. So it creates a delta P or a different pressure, a differential pressure from the moving process fluid. And people have done these using two insertions where there's a flow probe and a return probe, if you like. And what we've been looking at, where we've designed is one for a single insertion point. And so I'm just going to grab one of the ones sitting right here. So the idea is, and what we've looked at doing is first to do some computational fluid dynamics on this part that's going to face the direction of flow. It's not just an angled end or a curved piece. There's a specific geometry in there based on, again, some other research that have been done about how to get the maximum amount of flow and the minimum amount of differential pressure being created, or the minimum amount of back pressure being created when you have to make the flow make that 90-degree turn. Because for this device to work, the flow is going to be coming in this way, and it's got to turn and flow its way up the probe. And if we just did that by direct impact, there'd be some of the kinetic energy or some of the energy be lost in how that, in the sort of the non-fluidity, if you like, the non-consistency of the flow, the fact it has to stop and turn. So the curvature that's been built into here has been to optimize the idea that the flow is going to have to come in, round off that back wall and go up the tube. The idea then is it's going to run up the center of that probe. And so the flow that comes in that point is going to come out through the top over here. And now that can go out to an external device. It could be something like a vaporizer that's going to feed a GC. It could be an inline analyzer like a flow cell for an infrared or a Raman spectrometer. It flows through the analyzer and then returns back on this point. There's an internal tube inside here, I'm going to show you on a couple drawings from now, that separates the flow that's going out here from what's returning on the other side. It returns in the annulus and returns to the process on these two side ports.
Phil, is there a minimum process stream velocity required to operate this probe?
Yes. Now I know your next question is to me, what is that velocity?
It doesn't matter. We can talk outside of it, but just something.
We do have a brochure up on our website where we've done the calculations, use CFD to try to say, okay, if we took a light fluid, something like an LPG or an NGL with a viscosity of around 0.2. The big thing is the density of the fluid and the viscosity of the fluid. So with gases, it's really easy because they have low densities. And with low viscosity fluids, it's a lot easier because you get a lot less. You're going to be probably at fairly low velocities in here at laminar flow. So your friction factor is going to be bigger. So you want to try to optimize for that. So we have a couple charts up there that show for a given process velocity, this is how much differential pressure we think you can generate. So there's something to chat too. Material spec and temp. So So all 316 stainless steel. I'd have to go back and look at the actual spec sheet for what our pressure ratings were at different temperature. We'll put this onto 300 pound or 600 pound Nancy flanges. So you got to figure you're going to go up to 1,500 pounds at, probably 150 C, I think was the number. I'd have to.
149, yeah.
Pardon me?
149.
149. I was close, Jess. I was close. So yeah, so we've tried to design this along the idea of going on to, a typical process operating stream, crude oil stream, pipeline stream, where we're going to have to consider that, built for fairly high pressures, normally not that high at temperatures. You could derate it, and if you're doing if you're going to go do higher temperatures, you're going to probably have to start looking at derating because of the derating that's done for stainless. So the idea here then is that, Bernoulli's principle kind of tells us that wherever the velocity is the lowest, that's where the pressure is going to be the highest. So when we look at flow around a cylindrical object, what happens is where it impacts on the object, the flow essentially has to stop. So that's where the pressure becomes the highest. The fluid that stops goes around the sides. So all of the stuff that, if the pipeline had stayed flowing normally, would have flown without that obstruction in there, would have flowed straight along. All that fluid has to move around the probe now. So basically we have, we push some of the volume along there and we get a high velocity, and the highest velocity happens right along the sides over here. And that also corresponds to the lowest pressure on that side. So of course, the average pressure in the pipeline is going to be conserved, right? But at the impact side, we may see a higher pressure. In this case, I can't remember what flow rates this picture was done for, but we've got a high pressure in the front, and in a perfect world, we'll get a low pressure on the sides.
Okay, there's a good question.
Now you have great question. Yeah, ideally, it's always a frustration when you try to put things on sides. I end up showing almost all the pictures of this probe being vertical. In an ideal installation, you're going to put one of these in horizontally. The reason being that if you make it go vertical, whatever height you make it rise, some of the differential pressures now got to be used to get over that vertical change in hydrostatic head. And so the risk is if you have it mounted vertically, you may not have enough flow in the pipeline to get the loop to start to run because you can't get over the hydrostatic head. If you do get over the hydrostatic head, then the siphon effect works for you, but you might have to do something to actually get flow started. So ideally, we'd like to see these mounted horizontally. We've done versions of these, typically we're looking at going on things like a 4-inch or a 6-inch pipe for liquids. And for liquids, again, we'll use, this large cross-sectional area on the probe, so that we have a big throat to basically bring a lot of fluid in. For gas phase applications, I've got one sitting here. For natural gas applications, we've got a version that we've also made that's a lot smaller. I'll talk about this in a minute. It's a lot smaller entry, smaller ports on the sides, and it's just easier because you can go into a smaller pipe now with a smaller probe, and with gases, it's just easier to drive flow. You don't need as much differential pressure to drive flow. So the idea of this is the flow is going to stagnate at the front, accelerate over the sides, create high pressure at the front, low pressure on the sides, and we use that differential pressure to create a fast loop. So we'll create flow coming out, going around to whatever analytical device we have, and returning and coming back into the process. And so we can put some sort of analytical device here.
Oh, you got another question there.
Yeah. Okay, oh, good question. Yeah, certainly. Yeah, so the question is, isn't it easier to have liquids carry over if you mount it horizontally? Or are you using a filter in there? So with gases, we're not as worried about mounting it horizontally. So in a gas phase application, we don't have to worry about getting over that hydrostatic head. So in a gas phase application, we'd mount it horizontally or vertically so it can be self-draining. For liquids, we look at mounting it horizontally because then we worry about the density of the liquid and trying to get over the hydrostatic head. But with liquids, we don't have to worry about liquids carrying over now because in theory, we're a single phase stream, right? But no, typically we don't put a filter. We want to be careful about how we implement a filter because you're going to get pressure drop across the filter assembly. So we have looked at this in natural gas applications of using this to create the fast loop off the front side of a membrane filter, the fluid that doesn't have to go through the element. But you probably don't generate, in most applications, you probably don't generate enough DP that you can actually put a filter in line that you have to flow through. So just a couple of drawings to, oh, sorry. Another question, I just saw another question in there too. So after the analyzer will be almost no pressure or very low pressure. So how does gas go back? Great question as well. So some analyzers, like for example, water and hydrocarbon dew point analyzers, or things like, even if it's as simple as using something like one of those GE Panametrics moisture probes, an aluminum oxide jet probe. Some of those analyzers will operate at high pressure. And so for analyzers that can operate at high pressure, we would put them directly in line. So things like a dew point analyzer, an inline Raman analyzer, an inline infrared analyzer, we would put that directly on the high pressure loop. If we're going to be using an analyzer like a GC, what we would use a probe like this for is to create a fast loop that returns back to process. Stays, everything on that fast loop side stays at high pressure, goes across a filter element and pressure reduced and goes to the analyzer. So the analyzer vent would still vent to atmosphere. A question from Paul. How you doing, Paul? If you need to blow it back, if you need to blow it back, you could decide to, you got to try to decide where you think your contamination would be. If you are going to have to blow it back, and again, because you're going into you're going into a high pressure process, hard to blow back because you need really high blowback fluid. But you could, in theory, blow back through either port. A blowback from the top fitting is going to blow back through the center part of the tube, and a blowback through the side fitting here is going to blow back the annular region. So if you really were trying to say, I got to do blowback to concern myself with plugging, you'd actually probably have to blow back both sides. I suppose in theory, you could put high pressure gas in on, or high pressure fluid in on one side, and it's going to blow back both sides if it's over the process pressure, because it'll just flow around the loop. So from the drawings perspective, so just a couple of drawings, just kind of give you an idea of the internals. So the idea is we have this scoop-shaped tip at this end. It's welded onto the external piece of pipe. Internally, there's a piece of 3/4 inch tubing that's making a connection right here. And it's basically just a press fit type connection. So the fluid that comes in flows up the 3/4 inch tubing. The fluid that returns back, let's just do it in a different color. The fluid that returns back flows along this annular region, which allows it to get at these side ports and go back into the process. So this gives you just kind of an internal view, a front-facing view, if you like, and how it would be installed in the process. Again, showing it vertically, because if we showed it horizontally, it'd all be coming out of the page on you. So we then can weld a flange on to the external pipe, so adjusting the insertion length. Lots of good questions come up. We can adjust the insertion length with by where we weld this flange on. And so, of course, for different pipe diameters, just means we have to put the flange in a different position. I'm going to go back. From a MIT, recommended Reynolds number for crude pipelines application to obtain a representative sample. Seen probes with multiple scoop points. Now, does this compare to those? Certainly, if you're trying to see, it's going to depend a little bit on what you're sampling for, I suppose. Like when you're trying to do something like a water cut in crude, the concern is really is are turbulent enough? Are you turbulent enough that you can keep the water well mixed into the water? Of course, wants to separate from a density perspective and not being miscible. So, are you turbulent enough to keep the water in there? If you were running in a liquids application, the argument gets made. If you look at sort of a lot of books, people say Reynolds number or turbulence kind of kicks in around a Reynolds number of 4,000. A lot of people says that's just the beginning of turbulence. You really got to get above a Reynolds number of say 10,000. But certainly, whether you have a good well mixed sample is going to potentially be important in a lot of applications. Our assumption usually, whenever we're going to be using this to replace a standard quill type probe, which of course only samples at one point. And so if we were going to put this in place when we're concerned with mixing, we might consider putting something like upstream up here. We could put in a static mixer. So a static mixer is going to make sure that all the fluid's well mixed before it gets to that impact point on the probe. Flow back is going to be equal to the flow in, yeah, and assuming that I guess with whatever losses we may have had if we take some flow off to another external analyzer. But in general, if we just built a loop around this, yeah, you're going to have identical volumetric flow rates on the way back as compared to the way in. Our goal was to keep this pressure as high as possible, on the outlet side here, so that if we are going to put an inline analyzer, especially if we're putting in, say, an analyzer on a distillation tower bottoms, where the fluid might be right at its bubble point, well, then we want to make sure that we have minimal pressure drop on that feed through the probe side of it. So that's why we've kept all the diameters there for the liquid side as big as we possibly could. We haven't worried so much about the annular region causing a bit of pressure drop. Although, again, we still don't want to get much pressure drop there because it's going to limit our flow rates. But if we were to create any bubbles in that annular region, well, it's after we've already taken our sample off. Let's read a couple other things in the chat here, so I'm just going to go down. Is there a standard spec like flow with the density for water for a particular process velocity to obtain a specific delta P? I don't know if there's well, yeah, there is, I guess. If you build I think this is right, and I know Kevin's on, and he's way smarter about fluid stuff than I am. So if I get this wrong, he'll correct me. In theory, you get the pressure on the impact side is a half rho v squared, where rho is the density of the fluid, v is the velocity of fluid. The pressure on the low end, on the bypass side, is a half rho v squared. So in theory, if you do everything right in terms of your geometries and design, so you don't have any additional or unwarranted pressure drops, if you like, you're going to be able to build a delta P across this thing of the density of the fluid times the velocity squared, the velocity of the pipeline. So in theory, you could say that's the capacity factor you can use. Now, how much actual delta P you get is going to depend a little bit on process fluids and that. So again, one of the things that we did in the brochure was just generate some different curves for different pipe velocities and different densities of fluids. And we tried to go across kind of low viscosity fluids like, say, pentane, with viscosity around 0.2, and high viscosity fluids or intermediate viscosity fluids. I think we went up to a viscosity about 20 or 25. Thanks, Randy. Guess Randy's probably gone already. Cool. Okay. I think I caught up to all the questions in the chat. So adjustable insertion length available on 150-pound flange, 300-pound flange, 600-pound ANSI flanges. Okay. So, typical applications, where would we be thinking about using this? If we're trying to close couple some kind of an optical analyzer, I think it's an ideal solution for that. It lets us take something like a near-infrared cell or a Raman analyzer, something that can operate at high pressures, at process pressures, mount it right close to the probe, use this as a way to create a fast loop that we have continuous flow past that probe. We've installed them with a client who's doing composite sampling. When we're going to do composite sampling, you want to make sure there's a fresh sample always there in front of the pump. So by putting a probe like this in, we keep a continuous flow in front of the injection pump, and whenever it wants to put a sample into the accumulator, there's fresh process fluid there. Then one of the ideal applications for things like this in refineries is, what we often see in refineries and petchem plants, especially in a lot of the older installations, people have mounted a vaporizing regulator. So this is for a liquid stream. People have mounted a vaporizing regulator right at the sample tap. And the problem is, because these vaporizing regulator takes really low liquid volumetric flow rates, it can take a long time. We can end up with a big time delay on this side of the vaporizer. And so putting in a fast loop probe like this, if we were to take that same installation, I don't know how I can draw this here, but we'll see what I can do. If we were to take that same installation and have this probe that fed out and fed back in and create a loop that runs around it, and now mount my vaporizer right here, now there's a constant fresh feed right up close to that vaporizer all the time. And it's something that we can now vaporize and send as a gas phase over the sample.
Got a question there from Rocco too there.
Yeah, that comment, yeah. Ethane pipelines from moisture, liquids at high pressure, you have no place to return the sample, right? So, yeah, the big, the thing about this is it allows us to pull a sample and return it at the same pipeline pressure. Flare lines as well. I think this is a great thing to put on a flare line. If you're worried about emissions from your flare, you can create a fast loop with this from the flare side, and it keeps continuous flow going through there and allows us to return that past the process. So if you're worried about, well, what am I going to do with venting my flare, which might have high concentrations of H2S? Well, now I create my fast loop, and almost all the things that I vent are returned back to process. So again, up on our website, we have a brochure you can download. It has some of those pressure drop curves, as well as a bit more discussion of how this all works. And some of the figures I used in here were from the probe. And like I say, we'll also email out these slides. Well, the reason I put that product first is I thought it might create a lot of questions. And so allowable length from the T outlet to the inlet. So we did a lot of our flow rate calculations. So of course, the longer you go, the more pressure drop you have in the tubing that you run. So we tend to want to say, if you're going to run anything more than a couple of meters, you're going to want to make that fast loop be all done in probably 3/4, just to keep that delta P along the length of the fast loop run as small as possible. And I think the longest fast loop we looked at on the liquid side was 10 meters. So you don't want to create a really long fast loop with this because A, you're not going to get a lot of, you don't have a lot of delta P there. So you can't drive a really high volumetric flow rates. And if you want to get reasonable response times, you have to keep that fairly close. So again, it's one of the reasons why I say to go out to a vaporizer or go out to a locally mounted analyzer on the liquid side seems to make a lot more sense. With the gas phase, you can run it longer because there's so little pressure drop when we flow gas.